Hi, this is Jim McGuffin-Cawley from Case Western Reserve University, and the project that I'm going to be describing is really using infrared images from the modern day cameras processed in a way that allows you in real time to execute process control on existing mainstream manufacturing operations. I think there's been a lot of interesting work on identifying defects in materials using active thermography. And there's some tantalizing early publications about using passive thermography for actual process control that we should be able to extend and make a big impact with. It's really the result of computational speed, a lot of improvements in image analysis algorithms that are out there that makes this a practical thing. We think that you should be able to do real-time acquisition and then execute commands to a processing system in order to adjust the processing conditions to bring things back into spec. Partly it's hardware driven. The cameras are much better. They're more precise. They're also capable of looking at a broader temperature range, and partly it's the software behind them. The defect analysis I was speaking about, whether it's like gaps in a composite or detecting slag inclusions in a steel weld, has exploited what we call active thermography, where you induce a temperature change and then look at the response, sometimes an oscillatory one. But if you consider a lot of the unit operations that take place in manufacturing, there's a lot of natural temperature changes that take place where the part piece is either locally or volumetrically at a different temperature than the environment, and so the temperature is changing. I just have a short list here of the kinds of unit operations that would lend themselves to this sort of work. What makes this appealing for Case Western to be involved in is that we have a lab that has a lot of pilot plant level facilities that would allow us to do production relevant testing and data set accumulation. So our goal is really to look into IR images as a practical process control tool, to really work closely with industrial partners to make sure that our tests that we do in the basement of our building are meaningful approximations of what takes place in a production environment, and then ultimately we want to be able to generalize things. Quick look at some of the catalog. So we have this high pressure, what they call a squeeze caster, which is a light metal alloy casting machine that we can produce parts from. We could image, in this case, both the tooling and the part. We have some large-scale induction melters that will allow us to melt just shy of a ton of steel, and so you have a large enough volume of metal to work with so that you could look at things while you're transporting or moving the steel, as well as looking at the actual part. We have a fixtured metal inert gas welding unit that's connected to a plasma table, which is just a simple 4-foot square gantry system that would allow us to do reproducible trajectories of a weld in order to be able to generate large data sets. And then in our department, but under someone else's control, John Lewandowski, there's some metal forming operations which allow us to look at adiabatic heating of metal when it's being bent. So we've used this in the context of looking at additive manufacturing to repair tooling. It makes sense to extend it. One area where we're looking at this now is in qualification of die casting tool steels, and we take a water-cooled specimen and immerse it 20,000 times into a molten bath of aluminum, and we're able to show that we can take this long-standing test and we can augment the information that comes from it by adding thermography, otherwise not changing the test. We in no way modified the test. This just shows the inversion of some thermal gradients that take place in the short period of time that the tool steel is extracted from the metal. This is the first direct imaging of that we've been able to get. You can get a lot of information from this test. We can put very simple, straightforward numerical models to the test, and we can compare the results, and we find very good agreement. We are generalizing those simple models to be ones that include a catalog of different kinds of defects, different orientations of defects, and different locations of defects. What we're after really is to generate data sets that will allow us to really train the software, test the software, generate a set of results. There are not a lot of existing data sets. We think we can do that in a lab environment that is relevant to the production setting. We want to work then with the codes to process those. And ultimately, what this project would like to do is to deliver a comparison of the results of thermography control versus conventional control and evaluate it from a performance perspective, meaning how easy is it to use, how successful is it at its control. So with that, I will close this.